So, we will continue with the gravity based structures. So, I think as I mentioned in the last class, the primary purpose of gravity based structures was, one is the foundation design driven, the second one is the storage requirement. And in earlier stages of North Sea development, quite a few locations you see this kind of gravity based structures. One of the example is Kondip, the other one I think one of the largest gravity based system in North Sea. And basically we need to understand how it is constructed, means in comparison to the fixed type of steel structures. So this will be slightly different. It's going away from a framework wherein you drive piles. So in that case the requirement for construction and installation will be slightly different. As you can see here, concrete, as I mentioned, it cannot be constructed underwater for the several reasons that you cannot achieve strength. So you need to do a dry construction, of course, and then see how it can be installed. The major problem with this is a heavy weight, and we need to see how it can be transported, or in fact transferred from dry plus to water. In conventional jacket type of structures, we have several methods of deploying barges and then transfer by either by lift or by skidding, whereas here it's because of the weight. We will be talking about several 100,000 tons. So in such a case transfer becomes problem. So one of the simplest way is to float out. That means you require a dry dock wherein you construct this in a dry condition and then flood the dock, and it gets buoyancy sufficient enough to float itself, and you can either tow only the substructure or you can tow together with the superstructure placed on it, depending on the design conditions. That means the primary the design requirement will be buoyancy. So you have to manipulate the buoyancy in such a way that if you have too much of buoyancy, it's also a problem, because during tow, if you have substantial portion of the shaft as well as the superstructure is above water, not very good, because during tow your vertical center of gravity will be very important. The higher that you go, stability becomes more problem. So you have to keep this VCG as low as possible, but also have sufficient buoyancy to float out. So in such a case you should have variable ballast possibility, that at different situations you can ballast and you can remove ballast, so that things can be manipulated. So that is why you need to design these shafts on the bottom with all hollow cells which can be ballasted and deballasted. A typical concrete based structure, you can see here is a rectangular cells of many of them assembled together. So for us as a foundation engineer, what is important is the interface between the structure and the ground. So you can see it's a rectangular shape. So as far as when we want to construct or design a foundation, it is nothing different from a mud mat. What you have learned is exactly the same, because we don't have a skirt, and only difference is you got a large size structure instead of a mud mat of smaller size, you got a bigger size, and the material is concrete instead of steel, and that is the change that you are looking at. And then basically at different times you will get a different buoyancy, so the weight is going to be different. For example, when the whole gravity structure is sitting on seabed, in the initial condition no production is there, weight could be lower, and later when you are actually ballasting and then doing production, you may store oil and gas oil inside the shafts, the weight will increase on one side. So variable loading condition can exist. So that is something that you have to evaluate. So you can see here there are two types of cells at the bottom. The bottom is called base caisson or base foundation, you can call either way. It's just a rectangular structure which has got sufficient weight and buoyancy. So you can see open cells and closed cells. This is closed cells, always having provision for ballasting, deballasting, controlled manner, whereas the open cells will automatically get filled with water once you submerge them. But why they are requiring to be open? Because you can actually have possibility of ballasting solid iron ore, or you may actually dump rocks. Many times people dump rocks, granite rocks, or you can use iron ore, which will be even heavier than the basically the granite rock. If it is closed, it's not feasible. So that's why you keep them open, but then keep them open at what stage they provide buoyancy. It will be providing buoyancy in the initial stage. For example, in during the construction of this kind of gravity structures, you will be doing in a very shallow water basin. So that time once you raise the construction to this level, then you flood and you bring this one to a slightly deeper area and then start constructing the columns, because this height will help in achieving buoyancy to self support the bottom base caisson, and then after that when it comes to a deeper water area, this provides the buoyancy. So various sequences have to be worked out, and that is the major issue there. And it need not be 4 columns, it can be 3 columns. Sometimes you have 4 columns, but mostly the olden days North Sea platforms, most of them will have 4 columns. In fact, Kandip was 4 columns. So base caisson, base foundation structure, which is typically rectangular. You could also go for circular, which is more efficient in terms of bearing pressure, but then construction becomes little bit difficult. Open cell versus the closed cells, this is the purpose. The closed cells always have controlled ballasting, deballasting, which you can pump water or you can remove water from the cells, whereas the open cells only automatically flooded once it gets submerged. But the advantage is you have provision to go and fill up solid ballasting. Shafts, basically one each shaft can be used for specific purpose. One of them for risers, another one for drilling and basically interface between ground and the superstructure. The others can be used for utilities. For example, you may have to go down to inspect. So most of these gravity structures will have accessibility by means of either lift, mostly lift, or you may have other means. And then you can have a storage. So you can see each one is serving individual purposes. That means the center of gravity is not going to be symmetric. You may have actually one side heavier, the other side is lighter. So you can actually classify into hazardous and non-hazardous, which is not that much important for us as far as the foundation design is concerned, but of course which will affect. Hazardous means you will keep all the oil and gas or related activities in one side, so that the other side is non-hazardous, where you can locate all your safe facilities like living quarters and things like that, lifts. Deck connections, I think the interface is a little bit difficult, not like our because the superstructure is going to be steel, whereas the substructure is concrete. So you may have to find a methodology by which you can transfer the loads. Normally we go for the pin connections, and the scour protection is something very essential, because you have a large size rectangular structure which is sitting on seabed, and you can see here now scouring becomes a predominant activity, and you may have to do a scour protection by means of rock dumping or engineered fills around the structure. Typically the design of concrete structures is any civil engineering based calculations, but mostly we use because of the large hydrostatic pressure, it is designed using pre-stressed concrete, not conventional concrete. You know very well conventional RCC structures cannot span too much, and the loading also will be very limited. So that's why you go for a pre-stressing mechanism. Especially cell structures, pre-stressing is very good. You can take a large amount of pressure, external or internal. So that's why you normally most of the gravity based structures will be pre-stressed and can take any high pressure. And typically we need to design, because you are using this one for ballast deballast, you should have limitation on crack width. I think those who have studied concrete design will understand very easily that crack width is an important parameter for stress control in terms of actual crack as well as leakage proof, then corrosion protection of the steel reinforcement within the concrete itself. So you have to design in such a way that the crack width is limited to 0.2 mm, sometimes nowadays is 0.1 mm. As you can see, water retaining structures we go for 0.1 mm, especially like for example water tanks, but here the codes are not mandatory, but you can control the stresses in such a way that 0.2 is also acceptable. Shafts, which we have discussed various purposes and various classifications, I think need not be like this. This is only a typical example. It can be a parallel shaft, it can be a conical shaft, which depends on the design, but mostly conical, because the requirement is very limited on the top end, because the bending moments are going to be very small. So you don't need a larger size, because the larger the size, what happens is the sea wave attraction and the forces will be higher unnecessarily. So you normally try to taper it in such a way that the wave induced forces are reduced at the top, because you will see that the top area from water surface to 30% of water depth, most of the water particle kinematics will be very high and the loads are very high. So you can design using ISO codes, which is 19903 specifically for concrete based structures. How do we do analysis? This is something that we need to think about. It is completely different from what we were doing for fixed structures, soil structure interaction. So here is a large size concrete base. So the interface between the structure and the soil is going to be a special purpose device needs to be taken care. That means you, instead of putting pile soil interaction in the way that we were doing for tubular piles, we have to slightly deviate from there, because here everything is on the surface. Maybe you might have a penetration of few hundred millimeters due to settlement, but nothing more than that. So we have to devise a methodology by which soil springs can be modeled at the bottom of the foundation, and they cannot take tension, very similar to what we were doing for mud mat. But mud mat we go for a simplified method, not using pile soil interaction. So doing a simplified service analysis is going to be the case. So you can't be able to do a complete nonlinear analysis. You can simplify the nonlinear spring into linear spring, which we accept as a methodology for this type of structures. That means when you do a TZ curve, which you have already idea of how to develop a TZ curve, so you need to linearize and give that spring in here, and basically that will be the interaction between the soil and structure. Modal analysis basically to try to figure out what is the dynamic the frequency of vibration, which will be normally required for any offshore structures in order to find out the wave interaction with the structure. But most of the gravity platforms, since the foundation size is larger, you will not encounter any dynamic effect, because it will be very good, number one. Number two is damping is very high. So in such a cases you will not encounter. In case if you do, then you will have to multiply your loading to dynamic amplification factor by simplified means. Base caisson, which we were discussing earlier on, is used for two purposes: providing sufficient area for foundation calculation. That means the bearing pressure needs to be kept within control. The second purpose is to have variable ballasting. Third purpose is to have fixed ballast on the open cell. So that's what is given. The purpose of base caisson needs to be understood. So you should have provision for filling and removing, and also have sufficient area where bearing pressures can be kept within control, and also to control the deflection or the settlement of the foundation, you will have bigger size. So manipulation of the area, you can make it bigger or smaller, the spacing can be reduced depending on what is the load coming in. The typical installation, just to give you an idea how it is installed. So once the fabrication is done in the dry dock, you pull this whole structure into a slightly sheltered water and start making this construction of the shaft. That means the base caisson will be made in a shallow water or shallow depth dry dock, wherein you will have access to all the equipments, and you construct this. Once you raise the bottom caisson to the top level of this level, then you pull out into a wet dock, wherein you float out and start raising your shafts. Or if you have facility to float out completely, you can actually complete the shaft also in the dry dock itself and then float it out. Then once you bring to a right location where it is going to be either towed out or going to be installed, then you start ballasting the base caisson. Always do from one side, multiple ballasting if not possible. So you will see that depending on the ballasting direction, you will see the tilting. Then you go and counter ballast on the other side, so that it can be. So this needs to be calculated. At any one stage, the stability needs to be maintained. That means you do a GM calculation, make sure that GM is positive, and positive to a reasonable number, so that stability can be not compromised. So once you do all that, then you can set down on the seabed and it will sit. So basically this is a temporary condition at the time of installation. Now imagine the wave loads at that time could be smaller, because you are not going to install this at very high sea state. So what needs to be done now, you need to look for permanent ballasting. In addition to this, you need to see, because 100-year storm condition, horizontal load could be substantially larger. So that is the time you do a solid ballast at the bottom, which will make the structure heavier enough, and also install the superstructure. So this is the delta weight what you are increasing will be able to compensate for the overturning coming from horizontal loads of wave, current and wind. I think we have discussed about ballasting and seawater inlets. Basically just the utilities required to fill water and remove water, just a matter of interest. A typical picture just give you an idea how size wise is how much bigger than a conventional steel type of structures. So you can see here it's been divided into several compartments. I think already you should have an idea why we are dividing into compartments. You know, why not single compartment? Not normally very good, because redundancy will not be there. So if you have multiple compartments, even one damage may not cause substantial problem to the structure. So that's why you divide them into several sub compartments. So you can see here it is just done in a very small area. You don't even have a depth, too much depth, because once it's constructed to this level, you flood this area, because you got substantial amount of buoyancy which will start floating, and basically you can tow to another location, and you can so you can do it in a sequence, and then you do the raising of shafts, which is also very much shallow. I can see, because this particular project they were just trying to do everything and then float out. So this typically about 6 to 10 meters is the height of the base, and depending on the water depth, this could be 3 meter, 4 meter, up to 10 meter diameter shafts are constructed. So from the inside of the shaft, you can see here these are risers and conductors. You can see one of the shaft is utilized for that purpose, for drilling as well as for interface between the superstructure to the seabed. You can transfer oil and gas through risers. So you dedicate only for that purpose. So you can see on this, just on shallow water, because of this large size, you got enormous buoyancy. So it can actually support all the weight of the shaft as well as the bottom caisson. The draft could be 3 to 4 meters and sticking very high. But of course, when you are towing, you don't want to tow this high, unless during the tow route the sea conditions are very low. You have to actually ballast down, so that only small portion is sticking about. So depending on the design, you can tow either this way or tow with a higher draft. And you can see in the open condition, just it has come outside the dry dock. So initially it was dry and then have been flooded and has been floating, and you can tow using tugboats. It has come to open sea condition, so it's slightly rough sea. So now only you need to verify whether the sea conditions can be okay for stability, and calculation has to be made. And it's going through open sea condition with several tugboats assisting. And when it comes to the site, so you can see here the installation of the topsides. So this particular project, basically the installation of topside is at the site, not at the some of the projects they have done the topside also installed in the yard itself, and the whole structure together with the substructure and superstructure together is towed. Of course, only the buoyancy requirement is higher. The typical interface between the superstructure and the substructure, you will have such kind of receiving cones, basically for matting purpose, so that the load transfer is not critically injuring the concrete, because you see the concrete is brittle. So you need to have a good interface so that the load transfer is becoming easy. So that's why you have this shock absorbing mechanism by which the load transfer from this cone or from the superstructure is transferred to a multi-element load transfer into the concrete cell. So something very important. And basically that gives you an idea of a complete concrete based gravity structure. Sometimes we go for a composite or mixed steel concrete gravity structures. Bottom is concrete and the top is steel, very similar. That means you will have 4 jackets and one single concrete base. One of the project which I was involved in Turkmenistan is very similar. It's basically a large base concrete structure, and on top this 4 numbers of vertical jackets are installed separately. So that is a good idea, that minimizing the weight of the structure that is being transported. So typically the reason why you are going for this, the storage is not required in that particular field, storage is not required. What they require is a large size foundation, and the remaining can be steel, because once storage is not required you do not really need such type of structures. But still we need to go for gravity, because you got a very much shallow rock outcrop in which piles cannot be driven. So that is the one of the idea. So and economizing, basically installation wise this composite structure was economical and useful. So something like this, you see here 4 vertical towers with the superstructure, and basically the bottom some of them are relocatable. In fact, if you see this picture is relocatable, because this concrete gravity base can be lifted off after deballasting. So you can actually move like a jack-up rig, which I think we discussed about jack-up rigs in reasonable length in the previous course. Is exactly similar. I think we will quickly go. So the steel gravity based structures installation, again you can have 2 choices, either you can go together with the base and the steel gravity or the steel legs, or you can install the legs later on after you put the gravity base at the bottom. In this particular picture it is going together, so you can install them as very similar to a jack-up, except that the spud can is not individual, it is combined together. So how do we make a design of a gravity structure? Is very simple idea, logical sequencing. So establish the design weight of the superstructure, storage requirement, how much volume of storage and what is the weight of that and what is the location of it, estimate the weight of the base which will come from the soil mechanics calculation of allowable bearing capacity. So you can find out what area is required, and based on the area what is the weight required in order to get the stability, and you look for the dimensions and the shaft. So basically all 3 is making sure that weight estimation is correct, because that is based on which you are going to make the base dimensions. And then once you know the soil properties, establish the allowable or ultimate bearing capacity, work backwards to find out what size will give you the sufficient factor of safety. Once you do that, then look for the buoyancy, because you have several requirements of buoyancy. Buoyancy at the stage of construction, buoyancy at the stage of float out, buoyancy at this time you are just setting down, and at the last stage where the structure is on the seabed, you do not need buoyancy, but you need to be negative buoyancy. But how much is required in order to make sure that you do not get negative pressure? That means the tension in the soil's interface is not there. So that means you have to make sure that right compartment is flooded at the right time. You do not go and flood it different time, then you do not get it. So basically the buoyancy calculation is an iterative. Once you know the initial weight estimates, in fact this is what one of the problems we were trying to do in assignment or in the exam. So basically you should learn this procedure of trying to figure out what will be the requirement of buoyancy, what is the requirement of weight at what instant of time, and then if you have the buoyancy requirement, suppose if you have the top side also installed in the yard itself, your buoyancy requirement will be larger, and which will require to be exactly opposite when you set down, because you make too much of buoyancy, you should have sufficient compartments to ballast, otherwise you will not be able to set the structure on the seabed. So this initial, once you do the initial design procedure of trying to balance the buoyancy, weight and the size, then you go for actual design of concrete or steel elements, then redefine the weights and recalculate the buoyancy. So it will be several iterations before you could see a structure is complete. So in this stage you will find the foundation design come into picture. So your foundation design will have bearing capacity check, which is basically vertical equilibrium, and your sliding capacity, which will make sure that you have sufficient interface friction, or you will provide a skirt foundation. And then the third one is the overturning stability. That means your size of the rectangular base caisson will be determining basically if you have negative pressure, then you have to increase the size. Whereas we do allow negative pressure in case of mud mats, because it is only temporary, whereas in this case this is a permanent foundation, there is no other alternative. So you may not actually permit negative pressure. So that means you have to make the the foundation size larger enough. So typical picture of the gravity based structures being constructed. In this case you can see here one part of it is still concrete and having steel jackets on top, which was quite tall, about 120 meters or so. So part of it is concrete caisson. There is second part of it, because the top part not necessary to be that heavy, they wanted to minimize the weight, because the top soil about 11 meters was clay, and if you make it too heavy also problem, because settlement becomes issue. It's almost like a tubular jacket type of structures, and installed on top of the caisson itself. Typical picture of this under construction, almost going on to towing. I think at the installation site, matting almost done with installation. Various other forms of this type of gravity structures you can imagine, what kind of structures are required for making sure that stability can be achieved both in terms of installation and service. You can see here imagination, single large diameter shaft with a bigger base dimension. All that what is required, you can see here is only 2 columns, not necessary that you need to have 4, because the area requirement is smaller, so you can have 2, but again design needs to be make sure that in which orientation is better, because basically you need to have stability in this direction perpendicular, because if the sea waves are larger you will get the negative pressure at this side, which is not very good. So that is why normally we do not prefer 2, 3 means at least you can manage, but then 4 is always preferred, you will get a symmetry and also get better design requirement. Okay, so the next topic is pile group effects. I think you already have familiar ideas with PY, TZ and QZ. Also axial capacity of a single pile in single layer and multiple layers. I think all of you have already practiced, and constructing such diagrams for multiple layers, I think one of the example problem also you have solved. Now what we are looking at, you are not going to have a single pile for sure. The reason being, for offshore structures we have 4 corners, isolated foundations. Unlike onshore structures, you have a facility to distribute the foundations, either pile or shallow footings. Here we have got a group of piles going to be at one corner or other places. So when you have piles closely spaced, what happens to the load sharing? This is something that we need to take into account, because you can't put the piles very far. For example, you have a jacket leg and you don't put the pile foundation 20 meters away and connect them, because the load transfer is not going to happen. So always you try to bring the foundation closer to the load transfer location itself. That means you have one pile and put another pile in the vicinity. So what really happens when you have a pile, the load is transferred from the pile to the soil, and the soil stressed, and soil goes through deformation. Now you put another pile in the vicinity and that pile also transfer the load. So there will be a situation where the soil in between 2 piles will get loading from both. Now the calculations that we have made so far, we have not looked into it. What we are looking at is nobody else is in the vicinity, the soil gets only loading from one pile. That means the stresses calculated by whichever the method that we have learned is based on loading from one pile. If you get multiple loads from various piles for the same soil mass, that means it can't take, it will fail before what we expect. So how much is that, and whether this pile is close by or too far, we need to determine what is the better and what is the best for the current situation. In the case of onshore structures, we don't do this, we will just relocate the pile a little bit far away, so that we don't need to look at this interaction at all, because we got the flexibility in foundation design or basically distribution of loads. Whereas in case of offshore structures, such flexibility is not there, for the reason that I explained earlier, that mostly the loads are carried by jacket legs, and the legs in and around you need to locate the piles. Typically if you look at this picture, when you look at industry structures onshore, you will have several buildings and structures, mostly go for this kind of piling layout. You will arrange according to where is the loads, and you have a flexibility of locating them anywhere you like. So if you look at spacing, so this spacing matters because you bring them too close, you will have this problem which we were talking about, the interaction between piles. So the spacing of pile is going to be a matter. Now if you just go by rule of thumb, you keep them say 10 diameter away. For example, if you look at a diameter of offshore pile is 2 meter typical. So 20 meters away is too far for a jacket because the jacket itself will be only about 20 meters, 30 meters, 40 meters. So we have to bring them together by say 2 diameter, 2 meter, 2 diameter is 4 meter, 4 meter itself is quite far. So you can see the criticality of that, means it is going to actually not obtain whatever the calculation we make for vertical capacity as well as for lateral capacity. You bring in one number say 100 tons, but actual capacity could only be half of it because another pile is in the vicinity is going to produce similar effects on the soil. So that is something that we need to evaluate. Given the constraint, we need to calculate and apply. So that means instead of deciding the penetration as 100 meters, you may actually look for maybe slightly more depending on the contribution from other pile. So that is why it is called pile group effects, or the effects of pile spacing on capacities and deflections. So normally you decide on a spacing and then work backwards, what is the effect. We do not actually look at the effects and then position the pile, because the restriction of spacing on jacket is more than the effects, because you do not want to just keep moving the pile outwards because our capacity is reducing, because already we know we have to keep the pile very close, unlike onshore structures. So typically if you look at these pictures, you can see here this is the leg, one of the leg, and you got 2 piles attached to it. Now the distance between this pile to this pile, and also if you have a main pile, this pile to this pile has to be taken into account. In this particular one there is no main pile, so you actually can see here the distance from here to here is little larger, but this piles between the spacing between the 2 skirt piles are kept as much required. And also you can see here pile is added another pile because capacity was not enough, so you have 3 piles together. You could come up with any configuration depending on the requirement. So you can see here in this case it produces larger spacing because there is no main pile, but only skirt pile. You can see here the distance has increased reasonably, and in other places you have only single pile. So between this to this definitely will not be a problem because it will be already very large spacing. So the problem will be mostly associated with too many piles at one particular corner, and that is something that we need to look at. In some of the platforms, cluster pile like this, you see the piles are distributed around. When you go for this, basically when you are not allowed to go beyond certain depth, because you may have a very hard layer like sand, or you may have rock. So in such cases limit the penetration, increase the diameter or increase the number of piles. So increase diameter is not a very good idea because you may not be able to install. So increase number but reduce penetration and also reduce the diameter. So in such cases you will see, call it cluster pile. In some of the projects we have 2 more piles inside, it will be almost like a circular cluster. So you got so many of them connected together with the. So in these cases, should we take the capacity of this corner as the capacity of one pile multiplied by the number of piles. So that is what we normally do. We think if we have a group of pile, why not calculate the capacity of one pile and just simply multiply it by 5 if it is 5 number of piles, or we should look at a failure of the group of pile as a complete cluster failure. For example, you just make sure that you put all the piles together and you look at the perimeter diameter of combined action and times your length times your perimeter times the interface, the failure say friction between the cluster and the soil, which will be very similar to a pile calculation. So you make a calculation of group capacity and calculate the individual capacity multiplied by the number of piles. You see which one is smaller. The smaller has to be taken, because before the individual pile fails, maybe the cluster might fail as a total. So that is what is basically a issue if you locate them very close. So that is why we have to look at this aspect. So typically if you look at this picture, individual pile versus pile in the vicinity, you see here certain area of, if you keep them very close, almost overlap of stresses is going to happen from shallow depth, but if you keep them little bit away, you can see here most part of it is no overlap, but there is a overlap of stresses on a bottom part of the soil where the stresses are actually low. So basically that's, so this interface, what is going to be the contribution on reduction of the capacity on the first pile, which we are going to look at it. So that is something that going to be there for both vertical loading as well as for horizontal loading, and more problem is for horizontal loading, less problem for the vertical loading, because by the time the overlap reaches is this, the stress levels will be slightly smaller, whereas when you have a horizontal loading, the soil mass here will be almost affected in the vicinity quickly than the vertical loading. So that is why mostly for vertical capacity degradation normally we do not do it, but horizontal we have to be careful. So typical number you can see here, the stress distribution, or we call it the stress bulb at the bottom of the pile, is about 3 to 4 diameter will be more critical, beyond which is going to be almost less than 10% of the total stress. So you can see the last diagram, the third one, almost about less than 10%, whereas the first one you can see within the 3 diameter, you can see 80% of the stresses are going to be dissipated within the smaller distance from the pile surface. So that is why if you keep them more than 3 diameter, typically the issues are very less, especially for vertical loading. So that is why by rule of thumb, even the course also ask you to keep the pile spacing as at least 3 diameter or more, so that you can avoid doing all these calculations for the group interaction.